again, huh? So I see. Okay, no, yes, I appreciate the negative numbers. If you could go negative, then you could do, 500s and fractions and have a smaller sum, right? So, so I had said all positive numbers, but I don't know. So anyway, so if we do positive numbers, let's see, what do I see? Is that a 10 and a 21? Okay, 10 and 21. Let's see. 14 and 15. Is 14 times 15 equal to 10?
Yeah.
Yes. All right. 14 times 15. So those are slightly better than 10 and 21. 10 and 21 gives you a sum of 31. 14 and 15 gives you a sum of 29. So the best numbers would just be the square root of 210 and the square root of 210, right? So well done. Those are the ones that actually give you the smallest sum. But if I asked for integers, then it would be 14 and 15. If I asked for negative numbers, there'd be no answer because you could go to, negative 10 million times 1 over whatever, 10 million, whatever it is. Whatever fraction you have to multiply negative 10 million by to get 210, and you'd have our super small sum, right? So, so there's no solution if you go negative, so we don't usually go negative on these. Okay, so anyway, but I didn't expect you to know how to do it. It's just kind of a little warm-up lead into what we're doing today. Now, before we get into what we're doing today, I need to tell you about some changes that Ms. Grunwald and I decided to make last night. We had some time after school where the two of us were hanging out waiting. All right, so today we're doing section 4.7, which is optimization. So this is section 4.7, optimization. It's a big lesson, so we're going to kind of move. So 4.7, optimization. So I'm jumping right in with giving you steps. The steps were, just so you know, optimization is really just max-min problems with words. It's really all it is. It's word problems for finding maxes and mins. But there's still some good guidelines to know. So step 1 is obviously it's optional. Like no one is going to grade your picture, but it's helpful. So I personally always start by making sure I have a labeled picture. That's just helpful to me. You don't have to have it, but it'll help you. All right, so you draw a picture, you label it. You write the primary equation, which is the equation for whatever you're trying to optimize. If the primary equation has more than one independent variable, you have to find other equations so you can substitute out. We'll talk about this in a minute. Differentiate with respect to the independent variable, set the derivative equal to 0, solve, and then test to make sure you actually have the max or the min. For a minute. So the most common mistake that students make is reading these questions and writing as you go. Related rates, you kind of do that. You read the question and you kind of write as you're reading the question. Optimization questions, you don't do that. It's really important you understand. This is from years of experience. When you do an optimization question, you want to read the whole question, and you always want to start, after you've drawn your picture, you always want to start with the primary equation first. So this is where students mess up. Is they don't write the primary equation first. The primary equation is the equation for whatever you're trying to optimize. Optimize means make optimal. So usually it means finding a maximum or a minimum, the best or the worst, the greatest or the least, the highest or the lowest, the biggest or the smallest, whatever it is. It's usually some sort of an extreme. So the the primary equation is whatever you're trying to maximize or minimize, whatever you're trying to find the extreme of. No matter what, that's what you write first. And usually that's not given. Usually it's in the question at the end. So you have to read the whole thing and then kind of figure out, all right, what am I trying to optimize? That's what equation you write first. Once you've got that, then you look at it and you say, how many input variables do I have? If I have more than one, I got to get rid of them. Because, so related rates, you can have 50 input variables. It doesn't matter. As long as you have all the rates, you're just fine. Optimization is different. We're not differentiating with respect to time. We're differentiating with respect to our input variable. So because of that, you can only have one because you are in single variable calculus, right? So you need one input variable. So now you look for all other equations given in the problem, and so you see what you can use to get rid of any of the other variables by substituting. All right, then you don't differentiate with respect to time. You differentiate with respect to that variable because maxes and mins occur when the derivative is 0 or undefined, right? For these problems, it's very rare for the derivative to be undefined at the optimal point. It's almost always 0 at the optimal point. So I say set derivative equal to 0 and solve. If you want to take a look at the values that make it undefined, feel free to take a look at them, but it's very rare that they lead you to the right answer. I have to make a confession, and I'm going to put this on the video. I always skip step 6. I've never do it. So you're supposed to test to make sure your solution is a max or a min, because you can do all that work and it's asking for the maximum volume and you just found the minimum volume. So you could do that. It could happen. But if your work is correct, the problems are always written so that what you get is what you want. So I always skip step 6, but you are welcome to do step 6, which is where you just make a sign line and make sure it's a max or a min. Yeah, sorry.
On that AP exam, will they, I remember previously you told us they take a point if we didn't check. So will they do that here?
If they say they want you to verify that your answer is a max or min, they'll say it, and then yes, you should do it. But I will tell you, optimization problems, the ones that we're going to do today are book type problems, and every single calculus book does these same types of problems. AP, the College Board never asks these. They always ask them in a completely different way, which is why on Thursday we're going to do AP problems just so you can see what the College Board will ask. And it's never the ones that we're going to do today. The ones we're going to do today, you'll see the one on your test is going to be similar to what we're doing today. It's all these book problems that every calculus book always asks for, and they're good and they're interesting, but the College Board always asks them in a different way. So, all right. Okay, so we're going to start with a farmer. A farmer has 2,400 feet of fencing. He wants to fence off a rectangular field that borders a river. He needs no fence along the river. What are the dimensions of the field that has the largest area? So the first thing you're going to want to do, well, the first thing I like to do is draw a picture. So I draw a rectangle, and one side is the river. Pick a letter for this dimension. X. Pick a letter for this dimension. All right. What are we trying to optimize? Area. We're trying to optimize area. So our primary equation would be an equation for area. What would be the area of this field? X times Y. How many input variables do we have?
2.
How many do we want?
1.
All right, so now we look at the problem and we ask ourselves, gosh, was there any other information given?
2y plus
Ah, there we go. So they gave us this amount of fencing, right? Which basically is associated with the perimeter of our rectangle here. So if we have 2,400 feet of fence that we want to use for our field, then we could say x plus 2y equals 2,400. Is everyone okay with that? You all with me? When you solve to get rid of a variable, it doesn't matter which one you get rid of. You just need to get rid of one of them. So it doesn't matter if I solve for x or if I solve for y. I always personally solve for whatever is easiest to solve for. So if you had to choose between solving for x or solving for y, which variable would you choose? X, right? Because it's not that the y is horribly difficult, but it saves you from having a little fraction in your problem, right? So if we solve for x, we get x equals 2,400 minus 2y. So you're going to take this, and you're going to replace the x in your area function with 2,400 minus 2y. So we now have area equals 2,400 minus 2y times y. Personally, I find it easier to go ahead and multiply this out. If you don't want to, and you want to just do product rule for your derivative, that's fine too. Right? This doesn't matter. But I'm going to go ahead and distribute the y. So I have 2,400y minus 2y squared. All right, do we have a primary equation for what we want to optimize? Is it in terms of one variable? Okay, so our next step is to find the derivative and set it equal to 0. So go ahead and find the derivative, set it equal to 0, and then solve for y. Notice we're not doing dA dt, we're not doing dA dx, we're doing dA dy. It's not implicit. You just differentiate with respect to whatever variable you have. So my derivative is 2,400 minus 4y. I set it equal to 0. I get 4y equals 2,400, so y equals 600. What did the question ask for? What answer are they looking for? Dimensions. So the dimensions would be the x and the y. We found the y. How can we find the x? Yes. It's almost always your secondary equation that you're going to use to find your other variable. So you go to your secondary, because that's what will relate x and y. And I plug in a 600 for y. So x is 2,400 minus 1,200. So our x is 1,200. And my final answer would be 600 by 1,200 feet. Sometimes they'll ask you for the dimensions. Sometimes they'll ask you, like, what is the area? Whatever they ask for. You just make sure you read the question and answer what they're asking. All right. Not a bad little starting problem. Does that make sense? Okay, going to take it up a little notch. Oh, wait, before we take it up, I got to mention this. All right, so feel free to write this down. You have learned in this unit so far 2 types of extrema, absolute and relative. The only way that context that you've seen absolute extrema is on what's called a closed interval. So when you have found absolute extrema, what you were taught to do is find your critical numbers and test your critical numbers and your endpoints by plugging them into the original function. Biggest number is your max, smallest number is your min. That's absolute extrema on a closed interval. Relative extrema, you just make a sine line, and where the derivative changes positive to negative, you have a relative max, negative to positive, you have a relative min. What we haven't talked about is absolute extrema on an open interval. Now, why did your book decide to put this topic in this section? Because if we were going to check and see if what we find are actually maxes or mins, most of these problems, you'd be checking for an absolute max or min on an open interval, not a closed interval. So, when you're checking on an open interval, by the way, for absolute extrema on a closed interval, is there a because statement? No, absolutely not. You test your critical numbers and your endpoints, and you write your answer, and you're done. If you put a because statement for absolute extrema on a closed interval, you better watch out, because I'm going to check it. And if you say something like, because f prime changes from positive to negative, you've just justified a relative max, not an absolute, and I'm going to take off. So don't write a because statement for absolute extrema on a closed interval. However, absolute extrema on an open interval, you have to have a because statement. So I'm just going to do a quick synopsis of a relative max, or an absolute max. Oh, whoops. I lost my mind. There we go. Plus, minus, increasing, decreasing. So the only ones that we're going to be talking about in this unit, because there's a whole different way of doing absolute extrema on an open interval with multiple critical numbers. So that's a whole nother topic. So for you guys, if this is ever asked at all, and it's so rare, like honestly, if this ever showed up on the AP exam, it shows up maybe once every 10 to 15 years. Like, it's so rare that this shows up. But if it does, what they'll give you is they'll give you a function where there's only one critical number. So if I look at this sine line, I know that whatever f of c is, it's not just a relative max, it's the absolute maximum for the function. How do I know it's the absolute? Because this function is always increasing before that point, and it's always decreasing after. Does that make sense? So there's no way, it's like, it's not, it can't like swing back and go back up again. It can't. This is it. This is the only critical number. This is the only place where something can change direction, where anything interesting can happen. If this is true, then this has to be the absolute max for the function. So how would we write this? You would say the absolute max is f of c, whatever that happens to be, whatever the y value. Absolute extreme are always y value. So the absolute max is f of c, because you can't just say because f prime changes from positive to negative. That only justifies a relative max. You have to say because f prime is greater than 0 for all x that are less than c, and f prime is less than 0 for all x greater than c. You have to say it's not just positive to negative, but it's always positive before and it's always negative after. The other thing the College Board will accept is to say that f prime changes from positive to negative and c is the only critical number. That is kind of an equivalent statement. They do take that, but they don't ever, like whenever they're publishing scoring guidelines, this is what they'll put. So, and this is what your book has as well. So we might as well just all be on the same And then it would be the same thing for absolute min, just vice versa. Right? Okay. All right. We don't ask this on your test. It probably won't get asked on the AP exam. But your book stuck it in this section just because it seemed to mildly appropriate to put it here because of testing for absolute extrema in these word problems. So anyway, yeah.
So we only have to know it in the context of a closed interval?
Right. For your test, it's absolute extrema on a closed interval or relative extrema.
Okay.
Yeah, we didn't ask you any absolutes on open intervals. All right. Any other questions before we move on? So I feel bad because all I'm doing with this, honestly, is just throwing it at you and then moving on because that's all we're going to do with it. Okay. Someday, maybe later on this year, this will pop up. I have like maybe 1 or 2 AP problems that I've got this on it. So somewhere in our AP practice, this might pop up. So it'll probably pop up again somewhere. All right. So anyway, back to examples. We need to construct a box that will hold a volume of 60 cubic feet where the length of the base is 3 times the width of the base. See figure. If the materials used to build the top and bottom of the box, shaded in the figure, cost $10 per square foot, and the materials used to build the 4 sides cost $6 per square foot, find the dimensions that will minimize the cost to build the box. So we already have a picture and it's labeled. So step 1 is done. Well, for me. For you guys, you have to put in your notes. But for me, step 1 is done. So step 2 is to write a primary equation. What am I trying to optimize? Cost. So I need to write an equation for cost. This is cost. I need to write an equation for cost. What I want you to do in your groups is I want you to take the next minute and see if you can figure out an equation that would give you the cost of building this box. So our cost, let's start with the sides here. So I'm going to start with, oops, let me move this back. Okay. All right. So this side and that side. So the 2 sides of the box. So what would be the area of one of those sides? What's the area? One of those sides? XY, right? Okay. So we would have the area of the sides, but there's 2 of them. So 2 times XY. And then the cost of building those sides would be 6, right? Times 6. Okay. So it's the number of square feet times the cost per square foot, right? Okay. Plus, now let's do what I like to think is like the front and the back. So like this one, right? And then the one that's back here. So the front and the back of the box. So if we do the front and back of the box, so we're going to have 2 times. So what would be the area of the front of the box? 3x times y, right? So you have 3xy times, and then again, the cost for the front and the back is still 6. All right. Now we're ready for top and bottom. So again, we have 2 of them. What is the area of, let's just look at the bottom of the box. 3x squared. And then the cost for building the top and bottom is 10. This whole thing right here, that's our cost function. Does that match kind of what you guys figured out? Yes? Okay, let's clean it up. So we get 12xy plus 36xy plus 60x squared. So we get 48xy plus 60x squared. All right, so there's our cost function. How many input variables do we have? 2. How many do we want? 1. Do we have any other information that could help us? The volume is 60, right? So if the volume equals 60, tell me what's an equation to figure out the volume of this box? Yes, it's 3x times x times y, so 3x squared y equals 60. Which variable would be easier to solve for? Y. Please say y, right? Now, a little note, just a side note, pretend this x wasn't here and it was just 48y plus 60x squared. Then you could solve for x squared and replace the x squared with the x squared, right? But you've got an x and an x squared, which means you would have to get the whole root, which is kind of a pain. So, just solve for y. All right, so my y divided by 3 is 20 over x squared. So I go back to my cost function, and I get 48x times 20 over x squared plus 60x squared. Whenever you're doing these, before you differentiate, always clean it up first. So you get 960 over x plus 60x squared. All right, what do we do now? Really? We want a cost of 0? We want a free box? What do we have to do first? We have to find the derivative, right? We're not finding the dimensions that make us have a cost of 0. We're finding the dimensions that make our cost be a minimum, which means we need to find where the derivative is 0, right? So first thing you got to do is find C prime. So take a minute, find C prime, and see if you can find your zeros. So dc dx, so it's negative 960 over x squared plus 120x. If there's one thing I'm hoping you have figured out in this unit, it's that when you have to find zeros, you have to combine everything together. Like the letters LCD should just be like in your head all the time, like walking around, sleeping, you wake up in the middle of the night, you should be saying LCD. So I want you to get so ingrained in the habit of finding a common denominator that it's nature. This is just what you do. You're so used to it, it's automatic. All right, so we find an LCD. Now, we either find where the derivative is 0 or undefined. If the derivative is undefined, what's our x value? 0. So that would definitely minimize the cost of the box, right? Okay, except we have no box, and it wouldn't fit the problem because the volume wouldn't be 60, right? The volume would be 0. So that would be silly. So instead, we set the top equal to 0. And you get 120x cubed equals 960. So you get x cubed equals 8. What's the cube root of 8? 2. Now, this is a cube root, so there is only one cube root. If it was like an x squared, where you get a plus or minus, you can't have negative length. You don't have to write the plus or minus. If there's a context that implies that x needs to be positive, feel free to just write the positive, right? If there's context, you can answer in a sensible context, right? Okay, but in this case, it's a cube root, so it's just 2. All right, so x equals 2. So we found our x. Let's read what we're being asked for. What did they ask for? They asked for the dimensions, right? So a box has 3 dimensions, has length, width, and height. So now we know the width is 2, because x is 2. What's the length? 6. We need to find the height, the y. How do we find y?
Put 2 back into the 20 over x.
Exactly. So you end up with 20 over 4, which is 5. So our dimensions would be 2 by 6 by 5, or if you want to write in increasing order, our dimensions would be 2 by 5 by 6, and I think the units were feet. 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 All right. All right, questions on this? Okay, we're going to take it up a notch. Oh, before we do that, we're going to get to know each other. All right, so I'm going to... Book is really new. This is a book problem, but it's still dated. They're talking about flat screen TVs as opposed to non-flat screen TVs, which I guess, I don't know. I guess you could think of the curvy ones now, right? Yeah, but I have a feeling they mean flat screen as opposed to the old gigantic ones that we used to have to. The ones that you can't even give away, even thrift stores won't take them for free. Like no one will take those big old TVs anymore. So anyway, you just have to pay to take them to the dump. Okay. So a store has been selling 200 flat screen TVs a week.
Wow.
At 300, yeah, it's a lot of TVs. So maybe it's a chain, right? Okay, at $350 a piece. A market survey indicates that for every $10 rebate offered to buyers, the number of TVs sold will increase by 20 per week. Find the revenue function, which is quantity times price. Revenue is the money that a company brings in, right? It doesn't take cost into account. It's just literally how much money did they bring in. All right. How large a rebate should the store offer to maximize its revenue? So what are we trying to optimize here? Revenue. Now, there really isn't a picture to draw. It's not a geometry question. I am going to tell you how to do this, and the reason I'm going to tell you is because the way that you set up your primary equation often is kind of different than how you think you would set up your primary equation. So we want an equation for revenue. So we need quantity, which is the number of TVs we're going to sell, times price, the price that we're going to sell each TV for, right? The trick is knowing how to write your input variable. Once you are told how to write your input variable, then setting up your equation really isn't that bad. So here's the trick to this, and I'm just going to tell it to you. So we're going to let X equal the number of rebates that we're going to offer. X is going to equal the number of rebates that we're going to give to our consumers. So now, if X equals the number of rebates that we are offering, we're going to write a revenue function. So we're going to start with quantity. Quantity is how many TVs we sell. So we always, normally on a typical week, we sell how many TVs? 200. So we're going to sell 200, but for each rebate we offer, the number of TVs we sell increases by 20. So our total number of TVs would be 200 plus what?
20x.
20x. 200 plus 20x. So if we issue one rebate, we're going to sell 220. 2 rebates, we're going to sell 240, right? And they'll keep going like that. So there's our quantity. Now we need to figure out the price per TV. What do the TVs start at? $350. But this rebate is essentially reducing the price, right? So each rebate that we give away means we have to reduce the price of the TVs by $10. So our price would be $350 minus 10x. All right. Do we have a primary equation?
Yes.
How many input variables does it have?
1.
See, we can go ahead and just differentiate, set it equal to 0, and solve. So if you want to multiply it out first, that's fine. Or if you want to go ahead and just differentiate with product rule, either way, whatever works best for you. So I'm going to pause this and I'll come over and take questions. Okay. So let's see. We have 20 times 350 minus 10x plus 200 plus 20x times negative 10. All right, so there's my R prime. I'm going to clean it up a little bit. So I get 70, 0, 0 minus 200x minus 2,000 minus 200x. All right, so I'm going to set this equal to 0. So I get 5,000 minus 400x equals 0. So 50 divided by 4. All right, so 25 or 25 halves, or 12 and a half. Okay. All right, so did you guys get that? Yes? Okay. So let's read the question. How large a rebate should the store offer? Well, if the rebates have to be in multiples of 10, then the store should offer either 12 or 13. When you get that halfway, it means on either side of it, you're going to optimize your revenue. So they can offer either 12 rebates or 13 rebates. Either way, they're going to take in the same amount of money. If they don't have to be in $10 increments, if you can just offer any rebate you want, then 12 and a half rebates at $10 each would mean $125 off per TV, would optimize the revenue completely. So they would want to offer, a rebate of $125 to optimize revenue. That would be their best bet, is 12 and a half rebates at $10 a piece, $125 off. So. Right, that's what I said, revenue. Yep, that is true. We don't know how much they cost, but to maximize revenue, that's what we'd want. All right, last problem of the day, and I'm saving by far the best for last. Okay. Now, so years ago, we're talking a lot of years ago, for several years, I used to give a test that was nothing but related rates and optimization. And so it was just nothing but applications and word problems. And so I always gave it around Halloween. And so one year, for a couple of years, I used the same test. So one year I decided, just for fun, to write all of the problems in a Halloween theme, right? So it was a Halloween-themed application test, right? And so this is actually straight off of that test. Now, the first year that I gave this problem, it did not go well. So that's why you have all those hints added, was to help, because without any hints, like maybe 1 out of 100 students got it. So anyway, Michael Myers. If you don't know Michael Myers, this is not the Michael Myers that's the voice of Shrek. This is Michael Myers from the movie Halloween, the whole series of Halloween, the guy with the hockey mask, right? Anyway,
that's Jason.
No, different hockey mask, different mask, right? So anyway, okay. Oh, you're right. Michael Myers doesn't wear a hockey mask. He just wears a mask.
Yeah.
You're right. I'm sorry. Okay, thank you. So, yeah, because mine, yeah. No, mine's appropriate. He kind of has a Frankenstein mask. But anyway. All right, so Michael Myers is chasing his sister Lori along the edge of a straight river that is 40 feet wide. Suddenly, Lori notices that there is a fully lit police station on the other side of the river, 100 feet down from her current position. Lori knows that she can only swim at a rate of 3 feet per second, and she can run at a rate of 5 feet per second. She decides it would be worthwhile to use her vast knowledge of calculus to calculate the best route to take in order to get to the police station in the least amount of time. So she quickly pulls out her paper and pencil, and arg, her pencil broke.
Oh no.
How can you help, or can you help Lori calculate this route? How far should she swim? How far should she walk, right?
Michael a serial killer?
Yeah, do you not know Halloween? Michael's a really bad guy.
Oh, okay. I have not watched this. Is it a movie?
Yeah, the movie Halloween.
Oh, okay.
Yeah, famous movie from the 70s, John Carpenter.
I've watched
And-
too many old slasher movies.
Yeah. So, anyway, I'm going to pause this for a moment, though, just to give you a little side story. You can take 3 possible paths. Either she can swim straight across and then run. This minimizes her swimming distance, but it's the longest path, right? So we don't know if that's the best. Or she could swim straight from where she is all the way to the police station. That's the shortest path, but it's the longest swimming route, right? Or she can do something in between where she like swims to some spot in between and runs the rest of the way. Just kind of a little combination in between thing, right? All right, so we don't know which way is best. Lucky for us, we have some hints. Hint number 1 says break the 100 feet into 2 parts. So I'm going to break this 100 feet into an X and a 100 minus X. So we're going to break that 100 feet so that this distance, like from here to here, this is X. This distance then would be 100 minus X. Once you do that, you can create a triangle from Lori to that spot. So this triangle right here. So you have the legs of the triangle would be 40 and X. So if you think about it, whatever we solve for, if X is 0, that means she's going to swim straight across and then run the 100 feet. If X is 100, it means she's going to swim directly to the police station. If X is something in between, it means she's going to swim somewhere in between, right? So the whole point is if we find X, we're set. All right. We don't want to introduce any new variables, but we need to find the hypotenuse of this triangle because that's her swimming distance. Is there a way that I could find the hypotenuse of this triangle?
40 squares.
Yeah, just Pythagorean theorem. This is the square root of 40 squared plus x squared, or 1600 plus x squared. That's a plus. All right. We are trying to minimize total time, not total distance, total time. We want minimum time. Make sure we have enough. We have enough time. We do. Okay. But we only have enough time if I walk you through. So I'm going to walk you through this. All right. So we have to minimize total time. So I give you a little hint. All of her rates that are given to you are all constants. So no variable rates here. When your rate is constant, distance equals rate times time. So time is distance divided by rate. We want to minimize time. So her time would be the time she spends swimming, which would be the distance she swims divided by the rate that she swims at. What rate does she swim at? 3 feet per second. All right. Plus the distance she runs. How far does she run? 100 minus x divided by the rate that she runs at. What's that? 5. All right. So, and without the hints, I will tell you, like almost every single one of my students just died. Like they're like, Lori just died. That's it, right? So then I gave this hint, and then a lot of students got this, and then started doing all this messy quotient rule everywhere, right? when it's just a number on the bottom, please don't do quotient rule. Just write it as a coefficient, right? That's a square, that's a square. And then this would be plus 20 minus 1/5 x. So whenever you have a number on the bottom, it's not quotient rule. It's just a coefficient. All right, so we are ready to differentiate. All right, so dt dx, so you get 1/3 times 1/2 times 1600 plus x squared to the negative 1/2 times 2x. What's the derivative of 20?
0.
Okay, so plus, negative 1/5. So I should just put minus 1/5. That's okay. All right, so let's clean it up. So the half and the 2 can cancel. So we're left with x over 3 root 1600 plus x squared minus 1/5. All right, what do we need to find? In order, before we start finding zeros, what are we going to have to do? Combine these fractions. We need an LCD, right? All right. So our LCD is going to be 15 times this root. So we end up with 5x minus 3 times the square root of 1600 plus x squared all over 15 times the square root of 1600 plus x squared. The bottom has no zeros. The bottom is never 0 because x squared is always positive. So there's no solution to the bottom. So really all we're looking for is where the top equals 0. Whenever you have an equation with a root around the x, like an x inside of a root, and you need to solve it, always get the root kind of by itself and then just square both sides. So we have 5x equals 3 root 1600 plus x squared, and now you just square both sides. You get 25x squared equals 9 times 1600 plus x squared. So a little bit of algebra. So I'm going to go ahead and subtract the 9x squared right away. So you get 16x squared equals 9 times 1600. All right, so now if I kill off a 16, I get x squared equals 900, and x equals 30. I don't know why my students have a hard time with this. So x is 30. All right, let's take a look and answer the question now. The question that was actually asked was, how far should she swim and how far should she run? So we need the distance that she swims would be square root of 1600 plus 900, which is root 2500 or 50, right? So she should, it's hard to say, she should swim 50 feet, and it's hard to say, she should run, all right, so her running distance is 100 minus x. Our x was 30, so how far does she run? 70 feet. She should run 70 feet. So she's swimming 50 feet, she's running 70 feet. So she's going to swim to this point that's 30 feet past where she is at right then, right? So she's going to swim there, and then she's going to run the last 70 feet, and she'll make it, and they'll arrest Michael Myers, and then everyone's going to... Yeah.
What's Michael's rate? So what if he gets police station?
Yeah, I know. We don't know Michael's rate for all we know. Although Michael, have you ever seen Michael swim?
Walk really slow.
I don't think I've ever seen him swim.
Jason's the one that could like go.
Jason could swim.
Yeah, Jason could swim.
Yeah.